Okay, so let's graph these on Desmos and see what they look like. So x squared plus 5x plus 6 divided by x plus 1. So if we look here, we see x plus 1, that x minus 1 here is a vertical asymptote, right? So we have a vertical asymptote at x equals -1, right? And then we have some sort of slant here that looks kind of like a line, right? So you can kind of see that there. We zoom out, right? So, all right, now let's change this to x plus 2. So now if we look, x plus 2 is a line, but if we look here at 2, we can see that it's undefined. So this is a hole. So we got a hole at x equals -2. Okay, so we can see the difference there in between those two, right? So now it says rewrite the function so the numerator and the denominator are both in factored form. So if we do this and we divide this out like we've been doing, right? So x plus 1, and we divide it out, right? And so you could do it the other way. I'm just doing it by long division, right? But so x, we have x squared plus 1x. Change our signs. We have 4x plus 6, so plus 4. 4x plus 4. Change our signs. We see here we get 2 as a remainder, so plus 2 over x plus 1. So we can see here we have a remainder, which tells us we still have a vertical asymptote. And then this right here, I told you guys had to do with end behavior. So our end behavior here is actually a line or a slant. So if we go back to this x plus 1, right, we can see that we have a slant asymptote at x plus 4. There it is, right? Pretty cool. Okay, so now let's do the same thing for this one. So we'll change it to, x plus 2 into x squared plus 5x plus 6. So we have x squared. We have x. Change our signs. And then we have 3. And if you look here, no remainder. So when we have no remainder, this is our slant or our line. And we have a hole here because there's no remainder. So again, you can see if we change this to 2, it's the same as x plus 3, the line. Right? See that? We just know there's a hole at that -2. All right, so the graph of one of the functions below has a hole, another a vertical asymptote, and a third has neither. Which of these exists? So if we look here, right, this one, we know there's an issue in f of x, right? We know there's an issue at x cannot be -2, right? But if we look at the top here, x squared minus 4, and we factor the top. So x plus 2, x minus 2, right? What happens? Well, this x plus 2 cancels out. So that tells us this is a hole, right? If it goes away, if it cancels out, it's a hole. Okay? Now, so we know that's a hole. Let's look at g of x. So x minus 6 over x plus 3, x plus 4. Okay? So here, if you look, we have issues at x cannot be -3 or -4. Doesn't cancel out. So what does that tell us? These are vertical asymptotes. Okay, and then the last one here, right, has to be neither. And if you look, well, if you look at x squared, just the bottom, right? Because that's what's the issue. We can't divide by 0. So if we just look at the bottom and say it can't be 0, and we try to solve for this, well, it's going to be an imaginary number. Right? Square root of negative gives us an imaginary number, right? Which is not on a graph. So there is no hole or asymptote there. Okay? Let's look at 68. So based upon what you have observed so far, write an equation for the function that has the following features, right? Produce a different function for each part and confirm your answers. All right, so only one vertical asymptote. Only one vertical asymptote at x equals 3. So 1 over x minus 3. That's going to be a vertical asymptote there. B says we only a hole at x equals 3. So if we had a hole, we're just going to say 2 times x minus 3 over x minus 3. Again, it's going to cancel out. So we'll have a hole there. Right? Now we're going to have holes at 1 and negative 1. So C, we're going to have x squared minus 1 over x squared minus 1. I'm going to say times x now up top. So again, we'll have positive and negative 1. They're going to cancel out, but they'll have holes. Okay, D. We got a hole at 4. This is going to be x minus 4, x minus 4. Okay, and then in the graph of x plus 6. So we're going to put x plus 6 here too, so that'll cancel out our hole and leave us with x plus 6. Okay, E. We have a hole at 2 and an asymptote at negative 3. So again, x minus 2 over x minus 2 times x plus 3. So again, the hole cancels, and then it leaves us our vertical asymptote there. Okay, F. We have a hole at negative 2. So x plus 2 is going to cancel. That's our hole. And then the graph of x squared minus 9. Awesome. Okay, for each rational function in parts A through F, work through and complete the bulleted items. So state, domain, and range, in behavior, all the things. So let's look at these. Okay, A, we have 1 over, and I'm going to go ahead and factor this. So this is going to be x minus 4, x plus 3. This is going to give us vertical asymptotes at x equals 4 and x equals negative 3. Okay. Yeah. B. We're also going to have a horizontal asymptote at y equals 0. All right, B, we have x minus 4 over the same factor, x minus 4, x plus 3. Now we're going to have a hole at x equals 4. We're going to have a vertical asymptote at x equals negative 3. And we're going to have a horizontal asymptote at y equals 0. Okay, C. We're going to factor the top to x plus 4, x minus 4. Same factor on the bottom, x minus 4, x plus 3. Again, we'll have the same issue. We'll have a hole at x equals 4. We're going to have a vertical asymptote at x equals negative 3. And we're going to have a horizontal asymptote now at 1. Why? It's that leading coefficient rule. Remember, same first term, squared and squared, so it's 1 over 1. Okay, D. We're going to have x and x minus 1 when we factor it over x plus 3. So we'll have x equals -3 is our vertical asymptote. We have no horizontal asymptote. Okay, D, E, and F have no horizontal asymptote. Okay, you'll have a slant, but you won't have a horizontal, right? So E, you're going to have x minus 4, x plus 3 over x plus 3. Again, that cancels, so that's a whole. So x equals -3 is a whole. And then we'll have a slant at that x minus 4. Okay, F. We're going to have x plus 6, x minus 2 over x plus 3. So again, it's a vertical asymptote at x equals -3. And nothing else is going to cancel, right? So we would have a slant there if we divide that out. Okay, so 70, in the previous problem, you encountered functions with two types of discontinuities: points or holes, and asymptotes. Asymptotes can be horizontal, vertical, or slant. Okay, it just says check those, right? And then sketch those graphs using a graphing calculator. You're welcome to go do this, right? And then where do the discontinuities come from, right? So they come from, obviously, the rules we established with the horizontal. The vertical comes from the denominator, can't equal 0, and then a slant comes from that long division if there is no horizontal asymptote. Okay? So it goes on to talk about end behavior here, and that end behavior function. So that end behavior function is either the horizontal asymptote, or if there is no horizontal asymptote, it's the slant asymptote that occurs when you do the long division, which we've already talked about. Okay? Yeah. So then here's some more. You can rewrite these by doing, the division and getting these. Definitely something for you to try out, work on your own. And that is lesson 722.